Hi everyone. I want to talk a little bit more, survey the groundwork for quantum mechanics, and actually transition a little bit and talk about quantum electrodynamics in this lecture. And we'll get back to kind of the standard treatment, talking about atoms and how they work in the next lecture series. But for now, kind of want to go off the deep end a little bit. And if you remember in the last video, it talked about the Aronoff-Bohm effect, and that formula, that adjustment that was made to the de Broglie wavelength, in a sense, is really the analogy to the Lorentz force law, F equals QE plus QVB. And in electromagnetism, we have these two kind of fundamental things we need to know about. We need to know how charge reacts to the presence of an electromagnetic field, and that's what the Lorentz force tells us. But we also need to know how the charge generates an electromagnetic field, which is then experienced by a second charge, say. And that second thing is what Maxwell's equations do for us. So the total theory is really Maxwell's equations, which talk about how electromagnetic fields come to be, combined with the Lorentz force, which tells us how individual charges react to those fields. Well, the adjustment to the de Broglie wavelength does the thing about generalizing what the Lorentz force law does. What quantum electrodynamics does, QED, is really push Maxwell's equations into quantum mechanics. And it's the combination of the two. Now, the way it does this is not straightforward at all. And in fact, there are deep problems associated with doing things like this of a mathematical nature. I mean, it's just very complicated and leads to several contradictions. The simplest thing that you might imagine, that one might imagine doing, doesn't work. And so, what do you do as a consequence? And, quantum mechanics, was really put together by 1927. That's when Dirac published his papers, and is usually considered to be when quantum mechanics kind of came to be. Quantum electrodynamics, however, required another couple decades in order to really tease out the fundamental way in which things worked. And Nobel Prizes were gained, people were happy. One really accessible way of understanding this is through Richard Feynman's book called QED, The Strange Theory of Light and Matter. It's really a compilation of 4 lectures that he gave describing quantum electrodynamics at a very elementary level. And those videos are actually available online as well. You can just Google QED Feynman video and you'll find them. And so on this slide here, I want to introduce a couple of the basic ground rules for quantum electrodynamics, which are quite a bit different than what we've talked about so far. So I've been emphasizing the fact that we should think about particles as waves, as fields, and that is useful for quantum mechanics. Quantum electrodynamics, all of a sudden I'm going to backpedal, and we're going to be talking about particles again. And it's probably the easiest way to introduce it. It's the way Feynman does it. You do recover fields again once you've got the full theory, but in order to understand kind of how things work, it's best to go back to particles, and that way you can see where the fields themselves are coming from. So in a fundamental sense, what we've got is basically this Feynman diagram. The Feynman diagram describes how particles interact with one another. And in quantum field theory, which is what we're talking about, in quantum field theory, every fundamental particle falls into one of 2 categories. It's either a boson or a fermion. Bosons like to get together. They're gregarious. And they're also force carriers. The photon is an example of that. The photon is a boson, and the photon carries the electromagnetic force. Now, the second category of things are called fermions. Fermions are the hard stuff. Electrons, protons, the things that make up matter. And they are fundamentally exclusive. They don't like to be against one another. And that's what gives matter its hardness. Really, at a fundamental level, is that these electrons, they just don't like each other. And so, in a sense, it's not really right to use the word repulsion, because that carries the connotation of force. But there is an exclusivity associated with this fermions. And so, the fundamental pattern in quantum electrodynamics is given by this diagram, in which we have two fermions, and that's represented by the straight line here, and they interact via a boson. They exchange this boson. This electron here basically spits out a photon, and it's absorbed by its neighbor over here, and that mediates the electromagnetic interaction. So we start with this picture, and there's a whole set of mathematics behind this picture that it represents. But this is the basic idea. And so each interaction here can actually be decomposed into three more fundamental pieces. One where you've got a photon that moves from point A to point B, an electron that moves from point A to point B. And each of those are associated with a certain set of mathematics. And if you just focus on this and use the mathematics in quantum field theory, you recover all of optics, all of geometric and physical optics. If you focus on just the electron, apply all the quantum field theory math, you recover what we're going to be talking about as quantum mechanics. This interaction node, if you will, is how we roll in electromagnetism in the whole picture. So in a sense, this one picture is what is required in order to roll electromagnetism into quantum field theory. Now, of course, I'm skipping all the math, and the reality is I don't even know it all. But this is how things are going to work in quantum electrodynamics.